So in this video, I'm going to talk about inverse relations and functions and how to spot them, how to find them, and just kind of what they are. So first of all, I'll start with something that we all know. At least I think you all know that what an inverse operation is. For example, if I start with x and add 2, the inverse operation would be subtract 2. And the reason that is because if you add 2 and then subtract 2, you get right back to where you started. So we started with x, added 2, then we subtracted 2, back to where we started. So, and I think we could, with a little bit of thought, could come up with all the different inverse operations. Like, for example, multiplying by 2, the inverse of that would be dividing by 2, because that'll take me back to x. Or x squared, the inverse of that would be square root of x, because that takes me back to x. So there's the inverse operations, and then the idea of that is, like I've been saying, it takes you back to where you started. So if you think about, here's a relation down here that where we're saying that 1 goes to 5, 2 goes to 8, and 3 and 4 both go to 10. So if we were to write the inverse of r, that means that this would be 5, 8, and 10. This would be 1, 2, 3, and 4. And 5 would be taking you back to 1. 8 would be taking you back to 2. And 10 would go to 3 or 4. Because basically, like we said, it's undoes. It takes you back to where you began, right? Undid what you did. So another way to think about inverse functions is that the x and y's switch places, which would also mean that the domain and range switch places, and that's what you saw happen here. The domain of this relation is 1, 2, 3, 4. The range is 5, 8, 10, and then in the inverse function, or inverse relation, I mean, the domain is 5, 8, 10, and the range is 1, 2, 3, 4. Now notice in this example, r is a function because every input goes to only one output, but its inverse is not a function because 10 is going to 2 different outputs. So just because something is a function doesn't guarantee that its inverse is also going to be a function. So you understand what inverse operations are, and so basically what I'm by point I mean that your x and y coordinates are switched. So if I know that, for example, in the original function, the point 1 comma negative 2 is on that graph, that ensures that the point negative 2 comma 1 would be on the inverse of that graph, because every point, one way if we're thinking about graphically, one way to go from the original function to its inverse is just switch all the coordinates. In fact, there is a transformation that we learned in geometry. Sorry, Connor, you haven't had geometry yet. It says, it's called a reflection. So if we take the line y equals x, and we so let's say we have some function that looks like this. I don't know. So, and then maybe like that. So if we wanted to graph the inverse of that function, we'll use green. If we want to graph the inverse of that function, basically all we have to do is switch the x and y coordinates of all the blue points. And there's a transformation that does that. If you just reflect across the line y equals x, that will switch the x and the y. So that means the inverse of this, inverse graph of this, the graph of the inverse would look something like that, because that'd be the reflection across the line y equals x of that blue line. So that's another way to think about inverses, is just switching the x and the y coordinates, which in the big picture would mean that you could also say that you switch the domain and range. So if you have a, f of x has a domain, let's say, of 0 to infinity, for example, and a range of all real numbers, let's say, so from negative infinity to infinity. The inverse function, and the way we write inverse is like that. So if this would be the inverse function, that's a little -1 up there, which this can be a little bit confusing. That's not the same thing as this. This would mean raise f of x to a -1 power, which would be 1 over f of x. And if I put the negative inside that little between the f and x, that means we're talking about inverse. So if this is the domain range of the original function, the domain range of the inverse, you could just switch them. So that means oops, I didn't mean to do that. I didn't mean to switch the positions. I meant, so the domain of the inverse function would be from negative infinity to infinity, and the domain of the range of the inverse function would be from 0 to infinity. And this should make sense, because if we're just switching the x and y coordinates, that means all the items in the domain would go to the range, and all the items in the range would go to the domain. So hopefully all this is making sense. Really, the biggest task when we're talking about inverse functions is if I give you the equation of a function, like for example, f of x is equal to 3x plus 5 divided by 2, let's say. So let's say that's our function. And you want to write an inverse function for that. Well, all the stuff we've talked about could help. You're switching the x and y, and that doesn't really help you come up with the equation necessarily. But the inverse operations could help. So now, because in this equation, you'd ask yourself, what am I doing to the x? I am multiplying by 3. I'm adding 5. And I'm dividing by 2. So those are the 3 operations that I'm doing. So in the for the inverse function, I need to undo all those operations. So that means I need to divide by 3. I need to subtract 5. And I need to multiply by 2. Now, of course, we can't just do these in any order we want because of order of operations. There's a certain order you have to do them in. So we would go back to the original function and say, okay, what was done first? It looks like multiplying by 3 was done first. If you think about order of operations, if I plug a number in for x, what's the first thing I'm going to do to it? I'm going to multiply by 3. Then the next thing I would do to it, if I'm following over operations, is I would add 5. And then the final thing I would do is divide by 3. So now, when I'm undoing things, I can't undo it the same order I did it. I have to undo in the reverse order, because it's kind of like peeling off layers. You have to undo the outside first. And so really the dividing by 2 is the outside thing. So that means over here, I'm going to multiply by 2 first, subtract 5 second, and divide by 3 last. So that means I would start out with 2x, subtract 5, and then put the big fraction mark, because that's a grouping symbol, and divide by 3 on the bottom. Or another way to write this would be 2x minus 5 divided by 3. The key is to make sure that you're doing the multiplying by 2 and the subtracting 5 first. Okay? So now a nifty little trick you can do to So this is kind of, think of it intuitively how you would undo it. But another way to do that is you could take the equation and write it as y equals 3x plus 5, and using this idea that in inverse relations the domain and range are switched, or the x and y's are switched, you can rewrite this as x is equal to 3y plus 5. See how we just switched the y's and the x's? And then you can solve for y to get y by itself again. So the first thing I do to solve this equation is to multiply both sides by 2. So I get 2x is equal to 3y plus 5. Next thing I do to solve this equation is subtract 5 from both sides. And notice we're just clicking right up this. So that'd be 2x minus 5 is equal to 3y. And then the final thing we do is divide by 3. So that would give me 2x minus 5 divided by 3. And notice we get the same answer as we had up there. So that's a nifty little way to find an inverse function if you have the equation. So I'll just run through a couple more examples here. Let's say that, for example, f of x is equal to the square root of x minus 2. Well, that means, again, if you list them, you could say the first thing done to the x is subtract 2. And the second thing is square root. So that means over here in the inverse function, I'd want to undo the square root first. So that means I need to square first and then add 2 next. So that means I'm going to start with x, I'm going to square it, and then I'm going to add 2. Okay. And just for fun, let's graph this, because that's actually the next thing we're going to do. So notice if you plug in some numbers in here, like for example, if you plug in 1, you get a negative 1, which is not, we can't take the square root of that, doesn't produce real numbers. So I try plugging in 2, and I get 0. So that's, oops, wrong place. So right there's the point 0, 2. 2, 0, I mean. And if I plug in, for example, I'm going to plug in things that I can do, like I can take the square root of 4, so I'm going to plug in 6. 6 minus 2 is 4, square root of 4 is 2. So if I go over 2, 3, 4, 5, 6, I can go up 2. And another one that's easy to see is if I plug in 11, I get 9, the square root of 9 is 3. So if I go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I can go up 3. And what you see is a function that looks something like this. So then when I go to write this function, if I was to graph this function, you guys know how to graph parabolas. Let's see, that would be up 2. The vertex would be right about there. And you'd have something that looks like this. 1 up 1 over 2 up 1, 2, 3, 4. And you can see that these two are a mirror image of each other across this line here. Except for if we were to fully graph this, we would also do this thing here. And this is a problem that we have to keep in mind, that when I'm going from a square root to a square, again, when I'm undoing things, because this is a function, we only think about half of this. So this is kind of an odd thing that we over here we say that the domain of this x has to be excuse me, not the domain, I mean the range. The range y has to be oh no, I'm sorry, I was right. The domain x has to be greater than or equal to 0. So that means we cut off this part here. Because if you think about this guy, what's the domain of this guy? The domain is from 2 to infinity, and the range is from 0 to infinity. So that means in the inverse function, we know that the domain has to be from 0 to infinity. And of course, the range is going to be from 2 to infinity. But we can see that right there. So this is what told me I had to chop off half of that, the other half of the problem. And again, the way you'd say that by definition is you'd say that we're talking about this function, but we're limiting the domain because it came from the inverse of that. So anyway, that's the domain. We can, if we were going the other way, for example, let's say we started with y equals x squared plus 2, and the graph of that would look something like this. Oh no, it would look like this. Right? And the inverse of that would be y equals x minus 2 square rooted. But notice in this case I have both pieces, so it would look something like this and like that. No, whoops, I missed that again. It should be starting at 2. It would look like this and like that. Notice that's the reflection across the line, y equals x. But in order to get both pieces, I'd have to put in here plus or minus. But the problem with that is this is no longer a function now. So this wouldn't be, this is another case where the original function was a function, but the inverse would not be a function, it'd just be a relation because it doesn't pass the function test that every x value actually has 2 y values except for that one right there. So if we want the inverse to be a function, what we can do is just limit the domain of the first function. So then we leave it as square root of x. We cut this off, cut that off too, if we're really wanting an inverse function, because this, all the parts of the domain and range are still going to be there. So that's the domain. That's a little talk on inverse functions. So you should be able to do section, well, the homework on page 410 now.